All right, that's a full room. I had no idea that CSRF was going to be this popular, so I'm happy with that. For the record, that's good. So I'm really happy you're here to learn about the past, the present, and the future of cross-site request forgery. I actually did a PhD on CSRF, cross-site request forgery in short is CSRF. And when you start writing talk titles, the past of CSRF, then you kind of feel old. So this thing has been around for a long time. It's still a problem. It has shifted a bit, shape-shifted. Things have gotten better, but attackers found ways to make our lives miserable again as well. So that's essentially what we're going to talk about right here. The goal of this talk is that you walk away with a solid understanding of CSRF, a solid understanding of the variations, and you learn how to defend your applications, because that's the end goal, not how to exploit things. That might be useful and fun, but it's about defending your application. So if you're hoping for something else, I'm sorry, I'll have to disappoint you. Let's start at the beginning. What the hell is CSRF? Like, who here does not know what CSRF means? All right, that is very daunting. Everybody's like, yeah, CSRF, we know all about it. So I'm going to explain it anyway because I have the slides, so apologies for that. But CSRF, cross-site request forgery, is a cookie-based problem. So it basically means if you have a web application and you're using cookies to keep track of some form of authentication state, you might be in trouble. That's cross-site request forgery. And it exists because the browser is very liberal or naive when it's handling cookies. That's a legacy thing. And browsers happily attach cookies to outgoing requests regardless of where they're coming from. So let me walk you through a scenario of cross-site request forgery. I'm going to use Restaurant as an example. So a restaurant review application. I kind of like restaurants and good food and all of that stuff, so combining that with AppSec makes perfect sense. So my training app for courses and talks is a restaurant review application. Also helps that everybody in the world knows how that works, so that's very convenient. So what happens when a user goes to restaurant.com? They authenticate to the application. This is a traditional server-side app, by the way, like Java server pages or PHP or whatever, the thing we've been doing in the past, if you want to call it that. And you log in with your username, password, or whatever you're doing, multi-factor, and in the end you get a response back, you get a cookie. And that cookie tracks your authentication state. And I'm purposely being vague here because this can be anything. It can be a session ID, can be some client-side stuff you keep in a cookie, which is probably not a good idea, but people are doing it. Or it can even be some fancy token that is stored in the cookie. It doesn't matter what it is. It's based on a cookie. And whenever you create a new review, the browser is going to send a request out to the backend, and when the application is going to send it, and when the browser sees the request leave, the browser is like, hold on, this request is going to app.restaurant.com. I have a cookie for that. And it attaches the cookie to the request, and the backend will know who you are. They will open up the cookie, whatever is in there, like, oh yeah, that's Philippe from 2 minutes ago, bam, create a review for Philippe, and off we go. That is a normal, legitimate scenario. You can see at the bottom we have like this dirty form represented data, like old stuff from way in the past. But that's how this works in traditional applications. All right, so far, so good. What's the problem here? Well, CSRF comes into play once there is this established authentication state. Once that's present in the browser, the attacker can start launching CSRF attacks. And this happens when the user visits a page that has some attacker-controlled content. For example, you might visit funnycatpictures.com. Or in the case of food, you're going to visit maliciousfood.com. That's my evil domain. Malicious food has some images about evil food trying to trap you, which is actually really awesome that you can generate these things nowadays. And malicious food doesn't really look malicious. It just shows you some stuff, but behind the scenes, it has malicious behavior. Behind the scenes, the attacker is loading a hidden iframe, and in that hidden iframe, the attacker is creating a form, and the form will point to app.restaurant.com, and the attacker will automatically submit that hidden form, and it will trigger a request to our target application from your browser. You're the victims here. And when the request leaves the browser, there in step one, the browser is like, hold on, I have a cookie for app.restaurant.com, slaps it on the request, and sends it out. And the backend is vulnerable here. The backend is mistaken, and it's like, ooh, a request for a new review. It takes the cookie, oh, that's Philippe, creates the review, bam, and you get a response, and everybody's happy. Well, at least the attacker is happy, the app is naively happy, and the user has been victimized in this case. I know this is a silly example, like creating restaurant reviews. I mean, the restaurant business is cutthroat, but not that bad. But imagine this happens on a banking website. If this happens on sending emails, on all kinds of transactions, this could have some really serious consequences. All right? That is cross-site request forgery. What I want to do next is I'm going to use a whole bunch of demos throughout this talk to show you things in action, and so we can investigate what's happening, why things are happening, and what we are supposed to do about that. All right, so let's take a look at a CSRF example. For CSRF, well, I have a version of the retrograde application right here. It's a very simple restaurant review app, so there's nothing really special about it. We can log in, and in this case, I'm going to enable the legacy application, so we want some form-based endpoints. We'll talk about other types of apps later on. If you log in, we now have a cookie. You can see that we have a session ID stored here, and that session ID is basically how the server keeps track of who we are. So we can see some reviews. We can create a review here as well, like very exciting demo, I know. It's super awesome. And you can go back to the reviews, and we now have created a review. It's not a to-do application, so it's a little bit better, but you kind of get the idea. And you can see the request to create the review is right here. We call new review. It's a post request. No, it's a get request. This is a post request. It has a body, like a post body that is being sent, and so on and so on. That's normal traditional behavior. So how are we going to attack this? Well, if the attacker wants to target this, all they have to do is send a similar request from a different page in the browser. I have this malicious food page right here with some images of malicious food in this case, and that all the way at the bottom we have I have made it very explicit, the malicious behavior. It's supposed to be hidden, and there's going to be a hidden iframe somewhere. Apparently it's not showing, but there's a hidden iframe, trust me. What we can do now as the attacker, so I'm going to put on my evil hat. Here's the CSRF page with the images and blah, blah, blah. And here's where we include the iframe. And this iframe is essentially where we want to launch our attack. And right now, there's a post in here as well. So that's essentially what we can do to launch the attack. We have a form. We point the form to retrograde.com. We provide some hidden values that we want to include there. And that's how you would launch the attack against the application. All right, that's cross-site request forgery. If you would load this, you can see the request going out here in the background. This is the evil page, but the network tab shows the request. And you can see the payload is traditional CSRF working well, and that's essentially what's going on right here. That's how the attacker launches the attack. If you would go back here as the user, the victim user, and you would reload the list of reviews, you will see that our attack is now right here. That's cross-site request forgery. All right? That's not good, in case you're wondering. That's not really supposed to happen. All right, so takeaway number one, CSRF attacks affect traditional server-side applications. They have been a problem since somewhere in the 2000s. I don't know the exact date that somebody came up with this, but when they did, everyone was like, oh crap, that's not good. And we have been fixing CSRF ever since, basically. All right, used to be a real problem, still is a problem today, but we'll get to that in a minute. First of all, now that everybody's like, oh, CSRF, that's awesome, now I can talk about myself. I'm Philippe De Ryck, I'm from Belgium, and I'm a security expert. So I do security. I help developers understand security, simple or complex security topics, through trainings, courses, workshops at conferences like NDC Security. So I see some familiar faces who were there on the API security workshop on Monday and Tuesday. So welcome back. I also do consulting. I like to help people solve problems because it makes sure that whatever I'm teaching in trainings is actually relevant and useful. I'm an Auth0 ambassador and Google developer expert. These are recognitions from DevRel programs, so I don't work for these companies, but they like what I'm doing in the community and sharing resources, so they send me some free t-shirts every now and then, and stuff like that. And in return, I mention them on my slides. And then finally, I organize a course in Belgium called SecOpDev. And SecOpDev is a one-week course in person on AppSec, where we bring in speakers from all over the world, and they teach about application security. And it's really fun, it's really good. We have delicious food. It's Belgium, so we also have delicious beer after the course, so that's perfectly possible as well. So if you ever need an excuse to visit Belgium, this is how you can do it on your employer's dime. So keep note of that. It happens in June this year, so if you want to be there, make sure to look into that. If you want to grab a copy of the slides, there's a QR code you can scan. It doesn't point to a CSRF website, trust me, it just takes you to my website where you can grab a copy, but they're also on LinkedIn or Mastodon, and if you just go to my website, I'm not that hard to find, so you can grab it from there, so no issues. All right, that's enough about the intro. A very long intro. So let's talk about some real content here. So how do we stop CSRF attacks? Well, traditional CSRF attacks are stopped. Well, actually, there's a problem. We can't really stop traditional CSRF attacks in the sense that you can't detect which request is the forged one, because it looks identical. From a service perspective, you get two requests. One is legitimate from the application, one is malicious from maliciousfood.com, and they kind of look identical. And back in the day, somebody came up with a defense like, what if we can make the legitimate requests look legitimate? And then we can reject everything else, and that kind of solves the problem. And we call that synchronizer tokens. And it's not pretty, but it works. And the idea is as follows. The legitimate application will include a secret value in the form. Like it creates a secret value for this specific user, their session, and includes that secret in the form. And whenever you submit that form, it's going to be a hidden form field. You don't see it as a user, but when you submit the form, the secret is going to be in the data at the bottom right there. And the server will get the request like, a review for Philippe. Hold on. I gave Philippe this secret token before. Is it present in the data? Oh yeah, it is. It's the same one. Awesome. Then it must have come from a legitimate application because I put it in the page and nobody else will be able to read it from the page. The assumption is if an attacker can read HTML pages from different websites, you have a whole other bunch of problems. That's not CSRF. In that case, you're done and forget about CSRF. Focus on the other issue. That's more important. So that's essentially synchronizer token. So when the attacker comes around, the attacker can try and launch the attack and they can send the request and the cookie will be there. But they have to provide a token as well, otherwise it's not going to work. So if there's no token, well, here's the request. If there's no token, then the server is going to be like, no, there's no CSRF token here, go away, or something else. The attacker can guess, maybe, like the token today is 17. Very, very low chance that this will succeed, especially if your CSRF token is supposed to be random, like cryptographically secure, random, long enough, and all of that stuff. It's unguessable. It's basically a solid defense against cross-site request forgery. And that is how you prevent CSRF in traditional server-side applications. All right, synchronizer tokens are a good CSRF defense. They have some issues, like if you have 1 million users, you would have to keep track of 1 million random values in memory. That's probably not the best use of memory. So there's variations on this pattern that allow you to push it to the clients in a secure way. So I'm not going to talk about these things in too much detail, but just know that there's alternatives here as well. Awesome. What's the problem with this? Well, the problem with this is that developers have to implement this. And I'm not saying that you're lazy, I'm just saying that if nobody explicitly told you about it, chances that you have a defense against this are very, very slim. And we've seen that in the past as well. And some frameworks have started doing this by default, and Ruby on Rails was definitely one of them, the first one that started doing this by default. But a lot of applications built without modern and secure frameworks will not have that defense built in. And that means that they are vulnerable to cross-site request forgery. And that was a huge problem back in the day, like literally a very big problem. What if there's a better way to fix this, right? What if we can just fix the underlying cause instead of asking developers to start generating secrets and checking them and this and that? And the underlying cause would be the fact that the browser gladly attaches cookies to outgoing requests. That's a legacy thing. That's something they came up with, I don't know, in the 90s, and 15 years later, they were probably like, crap, we should not have done that. But here we are with cookie tracking and third-party cookies and CSRF and all of that stuff. And for CSRF, the answer is a same-site cookie. You have cross-site request forgery and same-site cookies. You can kind of see where this is going, right? I have a very good image that explains same-site cookies. That's a joke. No, this does not explain anything. For now, I don't think you have to worry about AI-based presentations on complex security topics. So we're good. Well, I'm good for now. I don't know why this one does not have a face, by the way, just eyes. That's very scary. And they look like potatoes, not cookies, but that's a different story. Anyway, let me explain same-site cookies in a way that actually does make sense. SameSite is a new cookie flag. Well, new. It's by now like 5, 6 years old. But it's a cookie flag you can add to a cookie, telling the browser this cookie should only be used for same-site requests. So whenever you set a cookie as a legitimate application, you add that same-site flag, you can see right there, and the browser will mark it in the cookie store like this is a same-site cookie. And whenever you send a request, what's a site, by the way? Very important detail. What is a site? The browser thinks about sites as the ETLD, like the .com, the .co.uk, plus one. So in this case, we have .com and retrograde. So retrograde.com is the site here. And everything under retrograde.com is considered to be same site. So whenever your legitimate application makes a request, it's going to go out, the browser is going to look at the request, like, hold on, it goes to app.retrograde.com. It is same site. Do I have cookies? Like, oh yeah, this one, and it's same site. Yeah, good enough. Bam. Attaches the cookie, it goes out, and the application knows who you are and creates a review. Everybody happy. You can see where this is going, right? The attacker comes around. User visits this maliciousfood.com, the attacker sends a request, the request goes out, the browser sees like, it's going to app.retrograde.com, I have cookies. Oh, it's same site. And this is a cross-site request. It's .com as well, but it's also +1, so it's, well, we're here. Malicious food is a different site. So this is a cross-site request request forgery, that's where the name kind of comes from, and the browser will not attach same-site cookies. So the backend in this case doesn't get a cookie, it's like, who the hell are you? I don't know what to do here, and the request will fail. And that's same-site cookies. Let's call that a present of cross-site request forgery. Same-site cookies are really, really good at neutralizing CSRF. They take away the underlying cause of the browser, just like, yeah, whatever, here's a cookie. Only for same-site requests will the cookie be present, and that's a good thing. It's actually so good that Google decided in 2020, like almost 4 years ago, it's going fast, almost 4 years ago, Google decided, like, yeah, this thing seems to work quite well. You know what we're going to do? We're going to make this the default cookie behavior. They actually wanted to do that in March 2020. That was a scheduled timeline. And then like the whole world crashed down because of some crazy pandemic. So Google was like, yeah, probably we shouldn't add to that by now breaking a bunch of websites. So they postponed it 6 months. And in August 2020, they flipped the switch on this behavior, meaning that all cookies without the same site non-attribute would be considered same site. That means that every cookie set by default, if you had a PHP app which has been running since like 2001, like most PHP apps, I'm very sorry, by the way, if you're a PHP developer. I'm going to get beaten up after this talk, but I'll escape through the back exit. Anyway, if you're building an app and you don't set any specific same-site attributes, Chrome is going to treat it as same-site anyway. That's what this means. So for 90% or something of users, all cookies become same-site unless you explicitly opt out of this default behavior. That's a massive step forward for cross-site request forgery protections. So let's take a look at what this means. If you have paid attention to my demo, you may have seen I'm using Chrome, and I did CSRF, and it still worked. That's because I'm a cheater. So what I actually did is I marked my cookie in my application here. I set same site to none to make it work in Chrome. So I explicitly opted out of this behavior, otherwise the demo would have broken and it would not have been very interesting. So what we can do now is we can make same site, we can set it to Lex. There's like 2 modes of configuration. That's a lot of details that don't really matter. But Lex is a good setting for most applications. All right? So what happens in our demo? Well, first of all, I'm going to remove the existing cookie to make sure we get a new one. There we go. Reload the application. Re-log in for the legacy app. And there we go. And you can now see here is the property same site in our cookie store. You have the same site property, which is now set to Lex. So this is marked as a same site cookie. All right? What happens to our attack? Well, first of all, we can still add reviews like normal. The quality of reviews is going down fast, by the way. But what happens if you launch our attack? Well, the predictable thing is going to happen. Let's reload the page. You can, excuse me, that's my mistake. I'm screwing things up now. So let me do this again. Well, you already saw what happened here, so that's good. I don't have to show you. We now get, we send the same request. It's a cross-site request going to restogate.com from maliciousfood.com, and it gets us a 403 forbidden. That's essentially because the server doesn't detect any cookie anymore, it doesn't know who we are, so we're not authenticated. It's like, yeah, I don't know what to do with this, and the problem goes away. All right, that's same-site cookies in action. Why did I set this to lags? I said Chrome does this by default, but other browsers do not. So that's why in the config, you still have to set it. You can't just rely on like, Chrome users are protected against CSRF and screw everybody else. That's not a very good strategy. So I would just recommend to set same-site on your cookies, and then every browser will respect it as well. All right? That's essentially how we mitigate cross-site request forgery. That's the takeaway here about Chrome, and so on and so on. Some of you are probably like, seriously, it's been, let me check, 20 minutes and we're talking about server-side apps, apart from those 2 PHP developers who were like, yeah, this is awesome. Everybody else is like, this doesn't really matter, right? What the hell? I'm building APIs. I'm one of the cool guys. And that brings us to API-based security. Like, what about CSRF for APIs? Well, CSRF is very, very relevant for APIs if your API relies on cookies. All right? And that sounds a bit weird, like, cookies are this very old 90s thing, our APIs use tokens and so on. That's true. A lot of APIs rely on other forms of carrying authentication state than something handled automatically by the browser. However, a lot of APIs rely on cookies, especially if you have a legacy application that is being transformed into an API-based application. It's not uncommon to rely on authentication state carried in cookies. It actually works really well. Cookies are very well handled by the browser, sometimes a bit too liberal, but overall, cookies work well. And if you're building OAuth front-end applications, if you were in my talk last year, you learned you shouldn't do that. And you switch to a BFF pattern, a backend for front-end. And guess what a backend for front-end uses? Cookies. So cookie-based APIs, while not the norm, are definitely not uncommon. They exist and they are not that rare. So what about CSRF with APIs? Well, I have some slides on that. You can have a API-based application. I refactored the slide. I changed this to a different icon. Check. And we now have an API-based application. Seriously, PowerPoint development is really, really easy sometimes. What does that mean? It means you log in one way or another by calling an endpoint, you get a response, a cookie is being set, and that cookie carries your authentication state. And whenever you send a request, it's now a JSON request, not a form submission. It's a JSON request to create a review. The cookie is there. The API extracts information from the cookie, knows that I'm Philippe, and creates a review in my name. All right. What about cross-site request forgery? Well, cross-site request forgery happens in the same way. The attacker can launch something from maliciousfood.com, can construct a form, and submit that form to an API endpoint. Which is like, what? Well, if you massage the data in the form enough, you can make a form submit data that parses as JSON. It's a very weird thing, but it works really well, and I'm going to show you in a demo in a second. But you can make a form submit JSON data to a backend. And if the API is a bit naive, it's like, meh, it looks like JSON and it parses like JSON, so it must be JSON, and bam, off you go. New review created for that user on an API-based application. All right? Of course, attackers have evolved as well, and instead of doing weird form things with like JSON submitting forms, you can also launch the same thing as a fetch-based attack. You can just write some JavaScript with a fetch request and send it to an API endpoint, and then you can write actual JSON instead of weird form stuff that looks like JSON, and that would also work in practice as a CSRF attack. All right? So that's essentially the danger with APIs. And at this point, you're thinking like, come on. Really? Well, yeah, really, this happens in practice. Here's a story from OkCupid, a dating site. They had an API-based application, relied on cookies, and accepted JSON-based requests from the attacker, allowing you to send messages to other users on the platform, which is one of the features that you probably don't want to enable on a dating website. All right, let's look at CSRF against APIs and defenses against that. Okay, so what we're going to do is, first of all, I'm going to reset my SameSite behavior. That's one thing. In the legitimate application, we're going to remove our cookies, and we're going to log in again. Now, if I don't tick this box, I actually get an API-based application because it's the same app. It just has two endpoints, a form-based submission, and the rest are API-based requests. So if you do this, we can look at the reviews. We can add a review, hello test, and submit this. And you can see that the post here now contains JSON data. That's essentially what the application is submitting and what the API is processing. That's essentially how the API works. Now, to carry out a CSRF attack against the API, we can do both approaches. So let me first do the form-based submission. So let's remove this form. That's the old one. We don't need that anymore. And let's copy-paste the one from below to submit JSON. You can see here, the trick to submit JSON is the name of the field is the first part of a JSON object, and the value of the field is the second part of a JSON object. And if you tell the browser to handle this as the content type text/plain, it will not encode any characters to like form representations. It will just take name, add an equal sign, value, bam. And that's the data you will submit to an endpoint. So we set it to text/plain. We point it to an API endpoint, /API restaurants1 reviews. We send a post request, and that should cover things. So let's save this and see if the demo actually works. Clear and reload. You can see here is a post request to a reviews endpoint. You can see the payload. You can see the equal sign right here. And Chrome actually recognizes this as JSON. It's a form submission, and Chrome, the parser in Chrome is like, meh, it looks good enough like JSON. We'll just parse it as JSON, and off we go. So this is a form submission hitting API endpoints, creating reviews. And if you would go back here to our Burger Master restaurant, you will see that we have our CSRF right here. That should scare you, by the way. If you're a bit more advanced as an attacker, so let's make the attacker a bit advanced, we'll disable the frame, we'll comment that out, and we'll do the fetch-based CSRF attack. So we basically have the same request, but now as a fetch request, and I'll launch it automatically after 2 seconds of loading the application. So let's do that, and go to the attacker page here, clear, reload, wait for 2 seconds, and boom, there's your reviews. Always happy when it works. There's your review. It's a fetch request now, and it submits that to the application. All right? In case you're wondering, that's not good. This is not good. How do you fix this? Someone, come on. SameSite cookies, yes, absolutely. SameSite is like I said, it takes the underlying cause away, so it doesn't matter how you send the request because the browser will simply reject it. So SameSite Lex, let's enable that again. Go back here, we have to re-authenticate because I'm a crappy developer, but no worries. And we launch the attack again. And you will see now that it succeeds because I'm also a crappy demo shower. So let's remove the cookie. The reason is that the browser still had the cookie, so it doesn't get overwritten with a new SameSite flag. So now it's a SameSite cookie, and now the request will fail when we send it because there's no cookie. 403, and it fails. All right? So SameSite cookies also prevent CSRF in API-based applications. What's the takeaway here? The takeaway is if your API relies on cookies for authentication state, you have to think about cross-site request forgery. Maybe you can get away with same-site cookies, that's a good thing, but it's something you have to actively think about. All right? So same-site cookies effectively mitigate cross-site request forgery attacks. So I wasted 30 minutes of your time to talk about CSRF, just to tell you like, yeah, CSRF is solved. It's no problem. We're done. So enjoy lunch. No, don't leave yet. It's not done. There's a little bit more to it. In the beginning, I mentioned this variation on CSRF, right? And the variation is actually becoming more and more popular. And the variation would be aptly named as a cross-origin but same-site request forgery. You would abbreviate that as CORF, but I'm not going to say CORF like 20 times. It really sound well. So cross-origin request forgery. What does that mean? Well, site was com plus one, like the etld plus one, retrograde.com, but the origin includes the full host name. And that means if you can send a request from a subdomain of the site, like evil.retrograde.com, and you send it to api.retrograde.com, it is same site. They both have the same site. It's cross-origin, and it's request forgery. And guess what's going to be present on a same site request? Same site cookies. So that's not good. So let's go back to our demo scenario. What does this mean? This means that if we take our exact same attack scenario that failed right here, and we launch it from a malicious subdomain, malicious.retrograde.com, it works. Because here's a post with a 200 OK. That is cross-origin request forgery. Wow, you really should be up here because there's a lot of people looking at me like I'm an idiot. It's like, what the? Who would do that? I mean, come on. Nobody gives somebody else control over a subdomain. What are you talking about? We trust our users, our developers. No, nobody will do that. Well, actually, you're absolutely correct. There's no good reason somebody would do that, right? Sometimes shit just happens. That's one thing that can happen. Or the more logical reason is maybe your DNS is not as tight as it should be. Maybe you've been using CNAMEs to point to all kinds of cloud properties. Whenever you delete something on Azure, you don't clean up the CNAME, which means you have a bunch of CNAMEs hanging around, dangling CNAME records, and that CNAME used to point to something, and now it points to nothing. And guess who's looking for those things? Attackers. And if they find something like blah.blah.pragmaticwebsecurity.com pointing to nothing, or to an IP address that is no longer assigned, and they assign something with that specific IP address, or they create a property on AWS, on Azure that matches your CNAME record, all of a sudden, they can access it through your DNS records, like what's the old.retrograde.com, pointing to something controlled by the attacker. And that's not good, because now the attacker controls something in your site, allowing them to perform same site request forgery against your applications. And if you're skeptical about this, this is becoming a bigger and bigger problem. Bug bounty hunters are looking for this. There's like a whole article on MDN, Mozilla Developer Network, on subdomain takeover. And companies like Microsoft really struggle in keeping track of all your subdomains. And I challenge all of you, if you have access to DNS records, look into your DNS records and you'll find dangling CNAMEs, trust me. Even I had one, and I don't even run real applications. Somebody contacted me like, hey, I found this, I don't even remember what it was, something, pragmaticwebsecurity.com, pointing to nothing, and I registered something there, and now I can do nothing really because I don't really have much running there. But still, it was a real problem. This is getting more and more common. So the conclusion here is CSRF is dead. Long live CORF, if you want to call it that. And I'm not joking here, like CSRF is actually mitigated by same-site cookies, that's true, and yes, we have really good CSRF defenses, but mitigating cross-origin request forgery, that's not that easy, because same-site is not going to protect you. And you're like, yeah, but you're making this up, right? You just had an hour to fill on NDC Security, so you just made up stuff in PowerPoint, and everybody's like, ha, 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 that's pretty funny, but whew, not a problem. Well, no, I'm not. Attackers are actively abusing this, and this is a story from last year against Grafana. So if you installed Grafana and somebody got control of a subdomain where that Grafana instance was running on the same site, they could attack that instance. Just like that. And full access, by the way. They could compromise your entire installation through this mechanism. This is not a joke. This is something that happens in practice, and it's really, really dangerous. But it's very weird, because this is not supposed to happen. Because if you look at the details of those stories, the reason that API-based applications are being targeted, it's because the API had a very specific vulnerability. And it meant that the API is accepting content types that they shouldn't be accepting. Because if you look at the OkCupid story, let me jump back a slide, actually. If you look at the details for that story, it said right here at the bottom, that it accepted posts with content type text/plain. So you're sending data. We submitted that form with text/plain. We're sending data to an API telling like, yeah, this is just plain text. And the API is like, let's parse it as JSON. Bam. And that's the problem. And that vulnerability is actually really, really common. And I'll show you, or I'll walk you through the details of why this problem exists and what you can do to fix it. And there's a couple of steps to take into account here. This is the more complicated part of the presentation, but also the last part, so no worries. What's the problem? Let's start by looking at the vulnerability. The vulnerability is, here's my post endpoint, or the definition of my post endpoint, and I did not specify a content type. And I also did a bit of extra effort to make sure the JSON parses as JSON. Let's leave that in the middle. There's plenty of stories that illustrate that this is a real-world vulnerability. What I should have done is I should have added a consumes equals application/JSON. And this will trigger a feature in Spring. This is Java Spring, a feature that will check the content type to make sure it's JSON, and otherwise it will reject the request. That's what I should have done as a developer. Now, what does this mean? Let's save this. This has zero impact on the legitimate client application. So our client, if we log in here as a user, still works because we actually did submit application/JSON, but nobody ever checked it. So now things are going to work. So let's add a review. There we go. All right. So that still works. The attack, however, is going to fail now. The attack is going to, here it is, it's going to launch. The attack is sent, and then we get like a 415 unsupported media type as an error. That's the framework, because we said like, hey, this accepts application/JSON. The framework is like, do a check. It's not application/JSON, go away. And that's essentially what's going on right there. That's expected behavior. And now our API is protected. Why? And that's the complex part, because of how the browser deals with cross-origin requests. Let's go to the attacker code. Try to stick with me here. We have specified content type text/plain. This fetch request is equivalent to a form submission. Like the actual requests, apart from the equal sign in the payload, are identical. And that means that if you send a JavaScript-based request with fetch or XHR that is exactly identical to what you can do with a form, the browser will just allow you to send it, because whether you do it with a form or JavaScript, it makes no difference. But at the moment you start doing fancy things that you cannot do with forms, the browser will be like, hold on, that's a new capability, that's CORS, Cross-Origin Resource Sharing, and we enabled that in 2009, so new is relevant, but it's probably before some of you were born, but that's a different story. But if you want to do something like this, you can, you're perfectly allowed to do that, a lot of applications do that. But if you want to do that, the browser will be like, hold on, that's something that we didn't allow before. So first, I'm going to ask the server for permission before I send that request. Because if the server has been running happily since 2008, again, that PHP server, it has been running since 2008, maybe it doesn't know that this is possible. Maybe it doesn't know about these new features, and then I don't want to compromise it just by sending this cross-origin request that before did not exist in the browser world. So this is something new, and the browser will ask permission first. However, there's a second feature here, and that's the mode. If you set mode to no CORS, you tell the browser, like, let's just pretend CORS doesn't exist. And the browser plays along here. It's like, okay, yeah, let's do that. It's 2008 again. Everybody's happy then. And when you do that, and you try to send this, the browser's like, yeah, man, but it's 2008. We can't do that. So it's going to revert back to something that it knew existed in 2008. So if you send this, no CORS, but a custom content type, which is something that doesn't work, it's not allowed, and we send it, the browser will be like, yeah, that custom content type, I can't do that, so let's just use text/plain, right? That's good enough. And you can see at the bottom that the API is like, no text/plain, that's not allowed. So this doesn't work. What can we do? Well, we can tell the browser, let's pretend it's post-2009 and CORS exists. We can do that, no problem. And when you tell the browser that CORS exists, the browser is like, oh, content type application/JSON, I'll send that for you, no problem. Absolutely. But I'm going to ask for permission first. And the browser is going to use an options request. That's the CORS pre-flight. The browser is going to ask the server, like, hey, man, I don't know if you've been updated since 2009, but here's what I'm going to do. I'm going to send you a request from malicious.restrograde.com, and I'm going to use post for that. And I'm going to include a custom content type header. What do you think about that? And in this instance, the server is like, what? I don't know. And the browser is like, ooh, sorry I asked, and it will not send that request. So you can see that right here in the options. So this is like a probe, an ask for permission, and the browser includes request headers. The browser basically says like, hey, I'm coming from Origin, I'm coming from malicious.restrograde.com, and I would like to send a post request, access control request method, and I would like to include a content type header in that post request. And the server, in this case, is not configured with CORS. It's newer than 2008. It's like since this morning, so it's pretty up to date. It's newer than 2008, but it doesn't have a CORS policy. So it doesn't know, or it knows that this is not allowed, and it simply says, By not responding positively, the browser says like, the server says like, sorry, hands off, and the browser doesn't send the actual request, and that's why you get the error right here. That's the error here. It could not be sent because nobody opted into this. That's essentially how you can use CORS as a defense. So by ensuring your API is properly implemented, requires the proper content types, this problem shouldn't exist in the first place, which tells you that OkCupid screwed it up, and Grafana screwed it up. Actually, in Grafana, they really did some effort to screw it up, because you should read the story. They did not accept text/plain, but their check that they did on the server, for God knows what reason, was like, if the content type header includes the word JSON, that's good enough for us. So there's a trick in the browser where you can send text/plain semicolon JSON, and the browser is like, that's text/plain. And Grafana was like, it contains JSON, must be good. And that was the bypass they had. It's really, really weird. All right. Now, saying things like your API should always check the proper content type is really good advice, but it also puts the burden on you. And if it fails miserably. There's a second problem. Sometimes you have a post request without a body, which also makes no sense, except that post is about state-changing operations, and one of the very common bodiless endpoints is a logout endpoint. So you have logout CSRF, where you would just call logout endpoints wherever you can find them, and you would log users out all the time, which is very annoying, but it's not supposed to happen. But if you don't have a body, you don't have a content type, and you can't restrict access, and so on and so on. And that brings me to the last piece of content. There's a defense in-depth mechanism you can use, or a configuration option you can use, to force the use of CORS pre-flights. So you can add something to your application that if the attacker wants to send a request, they are forced to use CORS with a pre-flight, which will fail because of your server policy and prevents those types of attacks. And this is a really, really sophisticated mechanism, so stick with me. We enable, here, a specific server-side handler, and it's called a CSRF header enforcer because it's a very tough name. And the header enforcer does one thing. It checks if your request contains a static custom header, X CSRF, or X the name of your dog, whatever you want to call it. You're absolutely fine to call this whatever you want, with a static value like 1 or 42 or true or Oslo is awesome, whatever works for you. That's basically how this is. Why does this matter? Because adding custom request headers to requests on cross-origin requests, I have to say, is not possible in 2008. It only became possible thanks to CORS. And whenever you want to do something that became possible thanks to CORS, the browser is like, hold on, I'm going to ask for permission first. And then the server is going to be like, no, thank you, and the problem will go away. So here, I have made the API vulnerable again, so I removed this. I added this restriction, and that means that if we log in again, so we have an active session. If you launch the attack, it's not going to fail with a 415 or 43, but this time, well, it's still going to fail. I should also update my attack or reset my attack. So text/plain and no CORS mode. So now it will trigger our CSRF header enforcer, and the enforcer is going to say, bad request, go away. That's the 400 you see there. So I could call someone here in front. So that's the 400. That's our defense kicking in, like, hold on. first of all, this was not supposed to happen, and second of all, the header is not present. So you think, you're like, yeah, but the attacker can add a header, right? How hard can that be? Well, if you add the header in no course mode, adding the header, it's not that hard. It's XCSRF. Well, it is hard. You have to type correctly. This is a normal keyboard. You should watch me on a phone. It's a nightmare. All right. So we can add this custom header and send the request, but we have enabled no course mode, and the browser will be like, we're pretending it's 2008. No custom headers for you. 400. So if we enable course mode, you already saw that in action, like, yeah, we can do course mode. But when we do course mode, the browser is like, let's pretend it's 2024, but I have to ask permission first, and the options will fail. And you can see that in the options, the browser is asking for permission, and it's asking permission to send a custom XCSRF header. And the server is like, I don't know malicious.restrogate.com, go away, please. The browser is like, okay, and that's it. And that's essentially how you prevent cross-site request forgery in APIs. All right? This mechanism works really well. By the way, one of the cool things, one more thing. The reason this works is because I've implemented the application in such a way that it actually does send that header. So if you look here on the headers for the legitimate application, I have this Angular interceptor that actually sends this XCSRF header on every outgoing request. Very easy, very simple. And this doesn't require a pre-flight because we're same origin. If you're same origin, that has always been allowed, even in 2008 or earlier. Same origin requests are pre-course, they don't require a pre-flight. So this has zero impact on your application, which is good. It acts as a solid CSRF defense against your APIs, which is also good. And you should also, of course, enforce the proper content types. All right? Good. This works in practice. I'm not just inventing this. Dominic, sitting in the back, has built Duende Identity Server, and they have a BFF library for OAuth frontends, BFFs, and they use this exact mechanism in practice to prevent CSRF attacks out of the box. So this actually is used in practice as well. Look at that, a practical talk on security. I hope. We'll see at the end with the cards. So, APIs can rely on CORS as a CSRF defense. So CORS, cross-origin resource sharing, is really good at helping you prevent CSRF against your APIs while enabling legitimate cross-origin traffic, because your policy can say like, oh, of course I want to accept things from supercool.restrogate.com, but not malicious.restrogate.com. That's perfectly possible as well. All right? So that's essentially what's going on here. You should check your APIs for these content type problems. They're more common than you might think. And it highly depends on the framework on how strict this is enforced. So write a test for your endpoints that if you accept application/JSON, throw it some text/plain with a JSON payload and see what happens. That should be a default test in your test suite to ensure your endpoints behave the way you think they should behave. All right. We're deep in the rabbit hole now. So before I send you to lunch, let's try and climb out of the rabbit hole with a nice overview of what you can do to protect yourself. First of all, if you're not using cookies, CSRF is not a problem. If you're using something else than something added automatically by the browser, there is no cross-site or cross-origin request forgery. I'm very sorry for wasting an hour of your life talking about something that might not be relevant. You will not get that back, no refunds. So, if you're using cookies or if you're relying on cookies, you have to think about CSRF protection. So I have a flowchart. Let's start with asking a question. Is the application the only one within its site? Like if I'm deploying restrogate.com, the front end on app.restrogate.com, and the API on api.restrogate.com, and there's nothing else, I don't have any other DNS records, then the application is always going to be same site with only itself. There's never going to be a second same site property. Then you can use same site cookies. Why not? But only if you can guarantee that there's nothing ever same site that might be controlled by the attacker. And the application itself doesn't count, because if the attacker can control the app, well, CSRF doesn't matter. They can just send whatever they want from within the app, and you're done anyway. So cross-site scripting trumps CSRF in that case. All right? In many cases, this is not true. In many cases, you will have additional properties within the same site, like the ETLD +1. And in that case, you have to apply other CSRF defenses. If you're a traditional application, traditional server-side apps, that's for the PHP developers in the room, there's no real mechanism that works well against cross-origin requests except the traditional application level defenses, like synchronizer tokens or a variation on that pattern that works well because it doesn't depend on siteness, cross-siteness or same-siteness. It's just tied to the session of the user. So that one will work well. There's plenty of implementation patterns, libraries offering that, so look into a defense like that. And if the application is not traditional server-side, maybe it's an API-based application. If it's an API-based application, you can use CORS according to the guidelines I discussed here in this presentation. The talk is recorded, by the way, so you can revisit the guidelines later on YouTube as well and take it from there. And if your application is not API-based, fuck if I know, man. Sorry about the language, they'll bleep it out later. Seriously, I don't know what you're building. Come talk to me afterwards and we can see if CSRF might be a problem there or not. All right, key takeaways. First of all, CSRF matters when you rely on cookies for tracking authentication state. That's takeaway number 1. Takeaway number 2, same-site cookies mitigate CSRF, but it has evolved into a cross-origin based attack that is same-site. Like subdomain takeovers leading to CSRF is, well, CORF is a real problem. And then third, if you're building API-based applications, which most of us, I'm guessing, are doing, then you can rely on CORS as a defense against cross-origin request forgery. My slide was too small to put the full words on there, but cross-origin, cross-site, it works against both, and it's a really good defense. And of course, you can combine same-site with the defenses I talked about here, if that's relevant for you as well. Thank you very much. Enjoy lunch and enjoy the rest of the conference.